what NASA found on Ceres' dwarf planet. For centuries, the faint light of Ceres drifted unnoticed among the stars, a small, slow-moving point in the constellation of Taurus. It was discovered on New Year's Day in 1801 by Giuseppe Piazzi, who at first believed he had found a new planet. And in a sense, he had. Ceres was the largest body between Mars and Jupiter, orbiting alone within the silent gulf of the asteroid belt. Yet its small size soon denied it planetary status. It became instead the first of a new category, asteroid, a term that implied fragments, leftovers, failed beginnings. For 2 centuries, that was how Ceres was remembered. A piece of cosmic debris, insignificant against the grandeur of worlds like Mars or Jupiter. But time has a way of restoring perspective. In the 21st century, NASA's Dawn mission would reveal that Ceres was not a relic of failure, but a world entire unto itself, a fossilized embryo of the solar system, still faintly alive. Launched on September 27, 2007, Dawn was unlike any spacecraft before it. Where most missions relied on explosive chemical thrust, Dawn sailed with a whisper, a blue beam of charged xenon ions, accelerated by electricity into a steady stream of momentum. This ion propulsion system, perfected after decades of experiment, provided only the force of a sheet of paper resting on a hand, yet it could burn for years, continuously, efficiently. Instead of fire and fury, Dawn moved through the void with patience, trading speed for endurance. Its mission was equally ambitious, to visit 2 worlds, the massive asteroid Vesta and the dwarf planet Ceres, and in doing so, to read the geological autobiography of the solar system's formation. The spacecraft was small by interplanetary standards, a cuboid about the size of a delivery van, its silver panels unfolding like wings to harvest sunlight across the vast gulf between Mars and Jupiter. At its core were instruments of quiet precision, a framing camera for imaging, a visible and infrared spectrometer for mineral detection, and a gamma-ray and neutron detector for tracing elemental composition. The mission's name, Dawn, symbolized more than a beginning. It spoke of origins, of the dawn of planets themselves. Dawn's journey began with gravity's gift. After a slingshot around Mars in 2009, it drifted outward toward Vesta, the second largest body in the asteroid belt. When it arrived in July 2011, it became the first spacecraft to orbit a body in that vast region. Vesta proved to be a differentiated world, with crust, mantle, and core, a planet that almost was. Dawn's instruments revealed a surface battered but complex, layered with volcanic flows and mountains taller than Everest. It was a snapshot of planetary adolescence, the stage between rubble and sphere. Yet even as scientists marveled at Vesta's mountains and craters, their eyes were fixed farther still. Beyond Vesta's orbit waited Ceres, a smaller but stranger object whose muted light and low density hinted at something no one expected: water. After 14 months orbiting Vesta, Dawn's engines reignited. With the unbroken patience of ion propulsion, it spiraled away, its gentle thrust altering trajectory by millimeters per second. It took 2.5 years to cross the remaining 400 million kilometers to Ceres. A journey so gradual, it seemed to unfold in slow motion. During that time, the spacecraft became a drifting sentinel of the inner solar system, a technological pilgrim, following the path of ice and stone. In March 2015, Dawn slipped quietly into orbit around Ceres, the first spacecraft ever to do so around a dwarf planet. The first images that reached Earth astonished scientists and the public alike. Against the gray, cratered surface, bright white spots gleamed like stars fallen to the ground. These luminous patches, concentrated within Ocakator Crater, reflected sunlight so intensely that at first they seemed artificial. Speculation ran wild. Ice deposits, salt flats, cryovolcanoes, something else entirely? Whatever they were, they spoke of activity, a sign that even here, in the frozen middle of the solar system, a world might still be changing. The approach phase revealed a landscape unlike any other. Ceres' shape was nearly spherical, an indicator that gravity had once softened and molded it, yet its surface was mottled with broad basins and mysterious ridges. Its color was muted charcoal, its texture dusty and fine. Unlike Vesta's basaltic crust, Ceres appeared composed of hydrated minerals, clays, carbonates, and ammonium-bearing salts. These substances form only in the presence of water. In an instant, Ceres had transformed from asteroid to potential ocean world. The first global map showed a surface scarred by impacts but softened by flow-like patterns, as though ice mixed with rock had once oozed and refrozen, erasing sharp edges. The average density of Ceres, only about 2 grams per cubic centimeter, confirmed it could not be solid rock alone. Beneath its crust lay a mixture of water ice and hydrated silicates, possibly overlaying a briny liquid layer, a remnant ocean sealed beneath frozen ground. Dawn's detectors found hydroxyl signatures across the surface and localized water vapor emissions, suggesting that Ceres still occasionally vented moisture into space. It was not a dead rock. It was breathing, however faintly. To map its secrets, Dawn descended through a series of orbits, each closer than the last. From 13,000 kilometers down to a mere 35 kilometers above the surface, the spacecraft traced a spiraling descent that lasted months. Its sensors recorded not just the light reflected by minerals, but the faint whisper of gamma rays and neutrons emanating from the soil. Particles that revealed the elemental fingerprints of hydrogen, carbon, and iron. These readings painted a portrait of a chemically diverse world, rich in volatiles, a place more akin to the icy moons of Jupiter than the rocky planets of the inner system. As data streamed back to Earth, the focus sharpened on Ocakator Crater, a 92-kilometer-wide basin whose floor glittered with bright deposits. The brightness was due to sodium carbonate, a type of salt that forms when salty water evaporates. Dawn's infrared spectrometer confirmed it beyond doubt. This discovery was staggering. It meant that briny liquids had once welled up from Ceres's interior and, in geologically recent times, reached the surface, leaving behind crystalline salt. In other words, Ceres was cryovolcanically active, a world that erupted not molten rock, but water and salt. Elsewhere, the spacecraft spotted Ahuna Mons, a 4-kilometer-high dome that looked like a solitary mountain. Its slopes were smooth, uncratered, and streaked with bright streaks of hydrated salts. This too was no ordinary volcano. It was a cryovolcano, a structure built by slow extrusion of icy material from below. Estimates suggested it might be less than 200 million years old, yesterday, in planetary terms. The realization was profound. Ceres, a small, dim world only 940 kilometers wide, had remained geologically alive long after it should have frozen solid. Every orbit deepened the paradox. How could such a small body retain enough heat to sustain liquid reservoirs? Some models proposed radioactive decay of long-lived isotopes. Others invoked the insulating effects of ammonium salts and clathrate hydrates, which lowered the freezing point of water. Whatever the mechanism, it meant that even the humblest world could harbor the ingredients of life: heat, water, and complex chemistry, in miniature. The mission also carried a quiet philosophical echo. Here, in the asteroid belt, a region once dismissed as rubble, Dawn found a body that blurred every boundary of classification. Ceres was too large to be an asteroid, too small to be a planet, too active to be inert, too cold to be dead. It was the missing middle, a world of thresholds. In its gray plains and glowing craters lay the story of what the solar system might have become if planets had stopped growing midway. For NASA, Dawn represented not only scientific triumph, but also technological poetry. Its ion engines, powered by solar arrays, had operated for over 2,000 days, the longest continuous thrust in spaceflight history. The spacecraft traveled more than 6.9 billion kilometers, orbited 2 worlds, and rewrote the map of an entire region of the solar system. Its silence at the end, when contact was finally lost in October 2018, was less a failure than a natural sleep. Out of fuel to turn its solar panels, it remains today in stable orbit around Ceres, a metallic moon circling a world of ice and salt, destined to watch forever the slow sunrise over Ocator's shining plain. Through Dawn's eyes, Ceres became something larger than itself. It was proof that the boundary between asteroid and planet is not a wall, but a gradient. That even the smallest bodies can evolve, differentiate, and host water in abundance. It forced scientists to reconsider the scale of habitability. Perhaps not only moons like Europa or Enceladus, but even dwarf worlds hidden in plain sight might conceal oceans beneath frozen crusts. In that realization lies one of NASA's quietest revolutions, the understanding that life may not require Earth-like planets at all, only chemistry, time, and a spark of internal warmth. As sunlight glints across its orbit, Ceres remains a subtle light in the telescope, as Piazzi saw it 2 centuries ago. But now, every flicker carries meaning. The bright spots that once puzzled astronomers are now known as the residues of a hidden ocean world. Beneath its grey mantle lies the whisper of salt water and stone, preserved like a memory of the solar system's youth. The Dawn mission revealed that the smallest places often hold the largest truths, and that even a world 1,000 kilometers wide can expand the boundaries of what we call alive. When the Dawn spacecraft first approached Ceres in early 2015, mission scientists were prepared for a dim, cratered world, another airless relic of the solar system's infancy. What they saw instead made them pause. From millions of kilometers away, a cluster of blinding white points gleamed against the gray plain of a vast basin. Even as Dawn's resolution improved, those spots refused to fade. They shimmered under sunlight, their brightness 100 times greater than their surroundings. The images, released to the public, ignited speculation. Some saw frozen lakes, others whispered of alien lights. NASA scientists, no less fascinated, gave them a name that suited their mystery: faculae, meaning bright spots in Latin. The place that held them was Ocakator Crater, and in its shining heart lay a secret that would redefine what a dwarf planet could be. Ocakator spans roughly 92 kilometers across and lies near Ceres' equator. It formed from a colossal impact tens of millions of years ago, an explosion that melted ice, fractured bedrock, and left behind a complex network of fissures. Yet even in that scar, nature created something strange and beautiful. The brightest region, named Cerealia Facula, occupies the crater's central pit. From orbit, it appears as a circular patch of pure white, surrounded by a halo of paler streaks radiating outward like rays of frost. Closer inspection revealed the light was not reflected by ice, but by salt crystals, specifically sodium carbonate, the same compound found in soda lakes on Earth. The presence of such material was extraordinary. Sodium carbonate forms only in liquid water that evaporates under low pressure. On Earth, it is the residue of drying lakes, the mineralized echo of vanished water. To find it on Ceres meant that liquid brine had once welled up from below. The impact that created Ocakator must have cracked open deep layers of ice, releasing subsurface fluids that flooded the crater floor. As those brines reached the surface, they sublimated into vapor, leaving behind gleaming salt crusts. The process might have repeated many times over millions of years, each eruption renewing the brightness like a cosmic heartbeat. Dawn's visible and infrared mapping spectrometer, VIR, confirmed this story with spectral precision. The light reflected from Ocator's bright plains carried distinct absorption features corresponding to hydrated sodium carbonate and ammonium chloride, compounds that require water and moderate warmth to form. Even more astonishing, the spectrometer detected variations in brightness over time, suggesting the process might still be active. This was not a fossilized relic of an ancient ocean. It was a surface still being shaped by internal chemistry. At such low temperatures, roughly minus 35 degrees Celsius at noon, pure water cannot exist as a liquid. Yet if mixed with salts and ammonia, its freezing point plunges dramatically. Such brines can remain fluid even hundreds of millions of years after a planet's heat should have faded. Beneath Ocakator's surface, scientists proposed, lies a reservoir of salty liquid trapped beneath a rigid crust. As pressure builds, the brine seeps upward through fractures, erupting as cryovolcanic fountains, not of lava, but of freezing water. These eruptions would slowly deposit salts onto the surface, renewing the luminous crusts that Dawn observed. High-resolution images from the spacecraft's low orbit revealed domes, pits, and fracture networks surrounding the central bright spot. These were not random scars, but patterned structures resembling volcanic calderas and lava plains. The brightest dome, rising in the middle of the crater floor, was christened Cerealia Dome. It stands about 400 meters tall and 3 kilometers wide, its summit cut by radial cracks. Everything about it points to cryovolcanic uplift, an icy analog of magma pushing upward. On Earth, molten rock would have erupted. On Ceres, salty brine did. Over time, the water vapor escaped into space, leaving the white carbonate residue glistening under the faint sunlight. Even after years of study, the brightness of Ocakator remained a marvel. Unlike other reflective materials in the solar system, such as sulfur dioxide or pure ice, the salts on Ceres do not degrade quickly under radiation. Laboratory experiments showed that fresh carbonate deposits can persist for millions of years, suggesting that the eruptions occurred relatively recently, perhaps as recently as a few million years ago, or even within the last 1,000. If that were true, it meant that Ceres is geologically active today, a startling realization for a world only 940 kilometers across. Dawn's gravity and neutron data added another piece to the puzzle. Variations in gravitational pull across Ocakator revealed a low-density region beneath the crater, consistent with a subsurface reservoir of briny liquid extending several tens of kilometers deep. Models of heat transfer indicated that radioactive decay of isotopes, such as potassium-40 and thorium, could provide enough warmth to keep this reservoir partially liquid. Combined with the insulating properties of salts and clathrates, it became clear that Ceres retained internal oceans long after the solar nebula cooled. The dwarf planet, once thought frozen to its core, harbored a living sea beneath its shell. The chemistry of those brines fascinates astrobiologists. Sodium carbonates and ammonium salts are basic, not acidic, and could create stable environments favorable to prebiotic chemistry. Ceres's crust also contains organic compounds, detected by Dawn near the Ocakator Crater, carbon-rich molecules that form the scaffolding of life. Together, these findings suggest a startling possibility. Ceres could be a habitable environment, at least in microscopic terms. It might once have hosted, or may still shelter, microbial ecosystems deep within its icy mantle. Even more tantalizing was the detection of water vapor plumes. The European Space Agency's Herschel Space Observatory, in 2014, had observed faint bursts of vapor around Ceres before Dawn even arrived. Although no definitive plumes were captured by Dawn's cameras, localized haze within Ocakator Crater was occasionally observed in certain lighting conditions. This may indicate ongoing venting, a gentle exhalation from the planet's interior. The idea that a body once deemed an asteroid could exhale water into space was almost poetic, a reminder that the line between living and dead worlds is thinner than we imagine. The mission's final descent provided the most intimate view. In its last year, Dawn dipped to just 35 kilometers above Ocakator's surface, close enough to resolve individual boulders and veins of material. The bright areas displayed intricate veining patterns, where salt had seeped through cracks and crystallized. Thermal readings revealed that some spots retained heat longer than others, consistent with recent resurfacing or sublimation. The crater floor appeared younger than the rest of Ceres's battered terrain, supporting the idea of continued renewal. One of the most compelling outcomes of Dawn's analysis was the discovery that the salts were not purely native to Ceres's interior. Their isotopic composition hinted at materials transported from the outer solar system, perhaps by comets or primordial fragments rich in ammonia and carbonates. This finding reinforced the view of Ceres as a bridge between inner and outer worlds, a hybrid planet whose chemistry ties it both to rocky Earth-like planets and to icy moons such as Europa or Enceladus. In this sense, Ocakator is not just a crater. It is a window into planetary evolution. Its bright deposits are the frozen fingerprints of hydrothermal activity, and its subsurface brines are time capsules of chemistry from the earliest epoch of solar system history. Studying them helps scientists reconstruct how water and organics moved inward from the outer regions during the solar system's formation. The same processes that made Ceres bright may also have delivered the water that fills Earth's oceans today. As Dawn's fuel dwindled in 2018, the spacecraft continued to orbit Ceres in silence, its cameras still gazing down at the luminous plains of Ocakator. When communication finally ceased on October 31st of that year, it was by design. NASA had chosen to let Dawn rest in perpetual orbit rather than risk contaminating a potentially habitable world. Its legacy endures in the images, the ghostly crater gleaming under sunlight, the salts reflecting eternity. Ocator's bright spots remain, even now, visible through Dawn's final transmissions, reminders that activity still stirs in the cold heart of the asteroid belt. They are the solar system's lanterns in the dark, proof that even the smallest bodies can surprise us, that oceans may hide where we least expect them, and that warmth, literal and metaphorical, can persist against all odds. Ceres taught NASA a profound lesson, that the boundary between asteroid and planet, between inert and alive, is not drawn by size, but by energy. As long as a world moves, reacts, breathes, even faintly, it participates in the same cosmic story as Earth, Mars, or Europa. Beneath its gray exterior, Ceres is still writing that story in salt and vapor, under the silent watch of a spacecraft that came to wake it, and stayed to dream beside it. Ceres occupies a unique and solitary kingdom, too small to be a planet, too large and complex to be a mere asteroid. It exists on the invisible border between the solar system's two great realms, the rocky inner worlds and the icy outer giants. To scientists, it is not just another celestial body, but a missing link, a natural experiment left over from the earliest chapter of planetary formation. To understand Ceres is to glimpse what might have happened had the building blocks of worlds like Earth and Mars never fully coalesced, frozen instead midway through creation. When the solar system was young, the space between Mars and Jupiter was a tumultuous nursery of collisions. Swarms of planetesimals, the seed embryos of future planets, orbited in the newborn sun's gravitational furnace. Yet something went wrong there. Jupiter's massive gravity stirred the region into chaos, preventing any one object from gathering enough mass to dominate the rest. The result was the asteroid belt, a graveyard of planetary potential. But within that chaos, Ceres survived. Unlike most asteroids, which are fragments of shattered rock, Ceres became round under its own gravity, achieving the shape of a true world. Its interior differentiated, separating into core, mantle, and crust, just as Earth's once did. In that sense, Ceres represents a planet that never quite finished being born. The Dawn mission confirmed this planetary duality in exquisite detail. The spacecraft's measurements revealed a density and gravitational field consistent with a layered structure. A rocky core, overlain by a thick mantle of ice and hydrated minerals, capped by a crust of clays, salts, and carbonates. This makes Ceres unlike any asteroid, but strikingly similar to icy moons, like Europa and Enceladus. Beneath its dark exterior, scientists believe, lies a remnant, briny ocean, still liquid in places. That single fact challenges our textbook divisions. Ocean worlds are not confined to the outer solar system. They can exist even within the asteroid belt, halfway between Mars and Jupiter. In this light, Ceres becomes a kind of Rosetta Stone of planetary evolution, a record of what happens when water and rock, heat and cold, meet in delicate equilibrium. Its chemistry tells of a world where the building blocks of life mingled freely. Carbon, hydrogen, nitrogen, oxygen, and sulfur, the essential elements, are all present. Dawn's instruments detected organic compounds near Ocakator Crater, suggesting that Ceres' crust still bears the carbon-rich molecules forged in the early solar system. On Earth, similar molecules seeded the origins of life. On Ceres, they linger as echoes of a potential that never advanced beyond chemistry. More than any other world, Ceres links the story of the inner solar system's dryness to the outer system's abundance of water. For decades, scientists puzzled over the origin of Earth's oceans. Where did so much water come from? The leading hypothesis now points to objects like Ceres. During the solar system's youth, impacts from hydrated bodies, perhaps fragments ejected from Ceres-like worlds, may have delivered the bulk of Earth's water. The hydrogen isotopes in Ceres' minerals match closely to those in terrestrial seawater. In a cosmic sense, our oceans may owe their existence to the silent chemistry of this small, icy dwarf. In this way, Ceres is more than a remnant. It is ancestral, a genetic link in the lineage of worlds. Its dual nature shows how the solar system evolved along two parallel tracks. Closer to the Sun, rocky planets condensed from silicates and metals. Farther out, icy moons and gas giants formed from volatiles and frozen water. Ceres straddles both lineages. It is half rock, half ice. Its mineralogy, an archive of both environments. It preserves the transition zone, the place where heat faded, water condensed, and chemistry diversified. To study Ceres is to examine the boundary between worlds, a frontier both literal and metaphorical. The implications reach beyond geology. If water-rich worlds like Ceres are common, and data from telescopes suggest that they are, then the galaxy may be filled with similar bodies. Small, cold planets with hidden oceans and long-lived internal heat. They may outnumber Earth-like planets by orders of magnitude. In that sense, Ceres is typical, not exceptional. A window into a vast population of oceanic dwarfs drifting through the cosmos. What Dawn revealed was not just the character of one world, but a blueprint for an entire class of habitable environments. Ceres' longevity also challenges assumptions about planetary death. Once thought to be inert, it has proven capable of sustaining cryovolcanism and chemical renewal billions of years after formation. The salts and organics observed by Dawn are not relics buried in ancient strata. They are fresh, exposed by geologically recent activity. Beneath the crust, slow convection of briny material may still occur, a heartbeat in ice. This persistence shows that even small worlds can retain internal energy far longer than expected. Size is not destiny. Chemistry and insulation can preserve vitality across cosmic time. To planetary scientists, Ceres is a master key. It unlocks questions not only about origin, but also about diversity. Why some worlds become barren and others fertile, some massive and some miniature. It shows that the raw ingredients for complexity are widespread, that habitability is a spectrum rather than a threshold. If Ceres could harbor briny seas beneath its crust for billions of years, then countless other worlds, even those we call asteroids or dwarfs, might do the same. The philosophical implications are just as deep. Ceres reminds us that the architecture of the solar system is not a hierarchy, but a continuum. Planets, moons, asteroids, these are human categories, useful but incomplete. Nature does not recognize such boundaries. It only builds, mixes, and transforms. Ceres stands as the perfect symbol of that fluidity. A planetesimal that learned the language of geology, an asteroid that dreams of being a world. In 2018, when Dawn's xenon thrusters finally fell silent, NASA chose to leave it orbiting Ceres indefinitely. The spacecraft remains there still, a silent sentinel circling above Ocator's shimmering plains, its solar panels reflecting faint light from a distant sun. Mission planners intentionally avoided crashing it, to prevent contamination of the brine-rich surface below. For perhaps millions of years, dawn will drift unseen, tracing an eternal ellipse above a world that once spoke to it in salts and shadows. It is a fitting ending, a partnership preserved in silence between machine and world, between curiosity and mystery. Yet dawn's discoveries continue to echo across science. They reshaped our search for life, steering attention from large Earth-like planets to small oceanic dwarfs, worlds whose warmth comes not from proximity to a star, but from their own internal chemistry. In Ceres, NASA found a prototype of habitability independent of sunlight, a reminder that life, if it exists elsewhere, might arise in darkness, nourished by salt and stone. Even now, proposals stir for future missions. Landers, drills, and orbiters capable of probing Ceres' subsurface ocean directly. Instruments could analyze brines, measure isotopic ratios, and search for amino acids, the molecular fossils of biology. To land there would be to step onto the threshold of planetary creation itself, a place untouched since the solar system's first dawn. For all its modesty, Ceres holds an immense truth, that the universe does not waste its creativity. Between the fiery heart of the sun and the frozen frontier of Neptune, it has filled every gradient of possibility with worlds that experiment in water, rock, and time. Ceres is one such experiment, a small success in a cosmic laboratory that has run for billions of years. Its story closes not in grandeur, but in grace. As the sun's light fades across the asteroid belt, the bright spots of Ocakator still gleam, scattering photons into space. Each reflection is a message, a flicker of salt, water, and survival, whispering across the void that creation never truly ends. In the quiet company of that light, Ceres continues to turn, a world between worlds, a relic that refuses to die. And as dawn circles endlessly above, the spacecraft and the dwarf planet remain forever bound, a reminder that even in the smallest corners of the cosmos, the great story of planets is still being written.